Okay, so each one of these has a gel covering it. They're little light pens. And I've been experimenting with collimated light again. Um, yeah, let's get closer. Also, my kitty was sitting in front of it. We missed it. He was cute. So, oh, I got in front of the light. So you can see that when the red and green mix, you get yellow. When the blue and green mix, you get cyan. And when the blue and red mix, you get purple. And where they all mix, you get white. See how the white kind of fades to purple? And yeah, it casts some really gnarly shadows too. So I was playing with that, and then when you add another one to the set, see how it zigzags? It goes up, over, up. It goes up, over, up, over, up, over, up. And then if we get it to line up just right, we can get it to go over again. And yeah, isn't that cool? Let me piece these together real quick. I will. I'm recording a YouTube video right now. Oh, sorry. No need to apologize. It's all good. Okay. So yeah, check out that beauty. Now, this is all handmade. If I could 3D print it, it would be a lot sturdier. But yeah, each one I add makes the beam tighter. So, hypothetically, if I could add an infinite number of these, and also if I could make like a really tight seal around all of the light sources, see how light is bouncing back? If I could make a really tight seal around all of the light sources and make an infinitely long version of this, it would produce a laser. Some of the light would redshift into oblivion, so it would get a little dimmer, but it would produce a laser, or a laser-like phenomenon. But since I can't, instead it produces this. And, well, let's look at the light source the other way around. See, it's kind of like that Coraline tunnel. That tunnel from the movie Coraline. Doesn't it look kind of like that? Rainbow Blast. But yeah, as you can see, red, blue, and green make up all the colors that exist. Well, all the colors that exist to humans. I love that lens flare effect. So yeah, because humans have red, green, and blue cones, and also white sensing rods. So yeah, it's pretty cool being a human. But actually purple is a really special color because it's the only color where we can tell the difference between red, blue, green, and the naturally occurring variant, because there is no naturally occurring purple. There's no wavelength that represents purple. So, it's really cool. But TV would be a lot different if we could actually see different wavelengths of light. Because to accurately reproduce how we experience the world, you'd need one of those things that can, like, mimic emission spectra from atoms. You would need, like, some really complicated equipment, like beam summation crystals and laser setups and weird stuff like that. Anyways, yeah. Anyways, so each one of these modules collimates the light, and it works because when the light is expanding, some of it expands into the next chamber, but some of it gets deflected and hits the next wall. And when it does that, 50% of it deflects forward and 50% of it deflects backwards and then bounces around some more. And that happens for each one of these in the system. So if we could cut out light leakage, the only thing that would cause us to lose light would be redshifting and absorption. So if we had the inside of this coated in like the ideal white material, and we had the this part perfectly like cut fit or like sealed to these light emitters, and then we had no light leakage at all, then what would come out the other end would be fairly laser-like. The difference between this one and the other one is this one is actually a planar laser, I believe. Like, it expands. Let me curve this piece of paper and then get under there. It expands in the up and down directions. But yeah. Whereas the other one I have is a point laser because it uses a corkscrew pattern. This one does expand along the X and Y axis. It just slowly collimates along. I mean, it expands along the Y axis, but it slowly collimates along the X axis the more pieces you add. So it's only going to collimate one way. Let me remove the blue. Just want to see yellow laser. Isn't that cool? That's just being produced with light pens. That's so awesome. Look at that. But you see how the red is sort of like a barcode? That's what this collimation pattern does. It makes it rectangular. So having all of these pens in there kind of obscures the fact that the ideal placement is right here. And that produces a rectangular wedge, which expands along the y-axis, but not along the x-axis. See? It stays about the same x width, even though it gets taller. So it gets taller faster than it gets wider. So it's planar. And then if we move this over to here, I think it's the same effect, but just different placement. Yeah, look at that. That looks so much like a barcode. Yeah. So then let's turn on the blue. Put that on the opposite end there. Now we should be making a nice purple. Look, they don't touch. It's just like a barcode. Two barcodes right next to each other. Now, we angle the blue to intersect with the red a little bit more. I don't know if we'll... Yeah, we're not really getting a purple, are we? If we put the blue... We put the blue right on top of the red, then we should get a purple, if we can get these to balance like that. Okay. No purple. Okay. Okay, now let's see what we get. Only the blue is coming through. So you gotta get the angle just right. Wonder if the red got pushed back too far. Now let's see. Let me turn off the blue. No red's coming through. Okay, let's put the red over here. Now red's coming through. And let's put the blue on. Yes, we've got a little tiny patch of purple right there. But there is beam divergence. So they only overlap at close distances, and then they separate slowly. Because it's the pattern that makes the beam, it's not the opening itself. Isn't that cool? I think that's cool. Light is fun to play with, that's all.